Thank you, Carrie, to getting us started. And it is my pleasure to introduce Dr. Cassie Peterson, who's going to be our didactic speaker today. Dr. Peterson is a behavioral scientist who develops and evaluates evidence-based interventions to improve mental health for caregivers of children with neurodevelopmental and neurological disorders, such as autism spectrum disorder, especially in rural and underserved communities. Dr. Peterson earned her PhD from Syracuse University and has been at Maine Health Institute for Research since 2008. She is the founder of the very popular research navigation program at Maine Health, and we thank her for that. Her research expertise includes clinical trials, digital health, community-based methods to enhance mindfulness and reduce caregiver stress. She also has extensive expertise in statistical consulting, clinical trial design, and mixed methods analysis. So Cassie, I'll pass on the mic to you, and thank you again.
Great. Thank you, Yvette. Let's see. So I guess I'll go ahead and share my screen. Mm.
And Cassie, when you're ready to pass the mic over to Bree, give me just one short time to introduce her.
Okay, that sounds great. Let me just share the other screen. Let me know when you can just see my presentation, not the notes and everything.
That looks good.
You can see that now?
Yep.
Okay, great. Well, welcome everyone. Thanks for having me today. The presentation that Bree and I are going to give is on biostatistics. And this is a presentation that we give a lot to clinical faculty in a course that we are the co-directors for, the Clinical and Translational Research course through the Maine Health Institute for Research. So it's pretty clinically focused, and we're happy to give that to you today. Hold on, little glitch. Okay, we're going to start off just by reviewing our learning objectives. First, we're going to understand why biostatistics are important for clinicians. We'll then move into reviewing 3 types of analyses and on to reviewing levels of measurement and common statistical tests. We'll then conduct some analysis and interpret results together as a group. So that's your cue to pay attention. And then finally, Bree will jump in and talk about assumption violations and solutions, excuse me. Again, like I said, this is a similar presentation that I give to the research course. And about 10 years ago, when I was beginning this presentation, a young man raised his hand and asked, why do we even need to know this? Which, is fair, and sparked a nice conversation among the group. So I decided to start off my presentation with a little bit of understanding of why this actually is important for physicians to know. And, this can be, of course, brought to the broader population, not just for physicians, but I liked this article. It's an older publication from 2009, but I think it nicely summarizes the topic. And this is just from a sample of about 130 physicians, and they were really just polled to find out, their attitudes, and their use of probability and statistics. About 90% of the sample found statistics helpful for assessing clinical guidelines and evidence summaries, explaining levels of risk to patients, assessing medical marketing and advertising materials, interpreting results of screening tests, and reading research publications. 79% considered statistics important to their daily work, And 63% agreed that there were activities they could do better or start doing if they had improved understanding of statistics, such as critically evaluating others' research and getting better at explaining and teaching others. Also becoming more active in research themselves. In the 90s, we saw a real boom in evidence-based medicine, where we're looking at clinical expertise, best evidence, and patient values all coming together. This really emphasized critical appraisal skills, including having some level of statistical knowledge. So this is a nice shift in the literature there. Doing your own research really kind of helped us understand how to conceptualize our questions and the relevance of statistics in doing that, and working with data analysts, which is also extremely important. So biostatistics really provide essential tools for analyzing and interpreting data in medical research and in clinical practice. Understanding biostats helps us to make informed decisions based on the evidence. And statistics enables us to evaluate the effectiveness of treatments, identify risk factors for diseases, and assess the impact of interventions on patient outcomes. So without proper statistical analysis, clinical research findings may be misinterpreted or biased, leading to incorrect conclusions and potentially harmful medical practices. So I'll now move on to reviewing 3 types of analysis. I'm going to start with the most basic level, which is descriptive analysis. Descriptive analysis, as the title indicates, it describes and summarizes the characteristics of a data set. So it involves measures such as the mean, median, mode, standard deviation, and frequency distributions. This really helps to provide insights into the basic features of the data, helping to understand patterns and trends. This type of information is what we typically find in a table 1 in a presentation or a publication. And it gives you an overall sense of the sample that your data represents and whether the sample is appropriate for the research questions that you're seeking to answer. The second type of analysis that we'll review today is estimation. Estimation involves estimating population parameters from sample data. This is where we would use techniques including point estimation or effect size and interval estimation, such as confidence intervals. It helps in making inferences about the population based on our sample data, such as estimating the population mean or proportions. So estimation statistics, or simply referred to estimation, it's the data analysis framework that uses a combination of effect sizes, confidence intervals, precision planning, such as power analysis for sample size planning, and meta-analysis to plan experience, analyze data, and interpret the results. The primary aim of estimation methods is to report an effect size, or a point estimate, along with its confidence interval, the latter of which is related to the precision of the estimate, which we've seen as the 90, 95, and 99% confidence interval. And the confidence interval summarizes a range of likely values in the underlying population effect. Examples of effect sizes include the correlation between 2 variables, the regression coefficient in a regression, the mean difference, or the risk of a particular event, such as a heart attack, happening. And effect sizes complement statistical hypothesis testing and play an important role in power analysis, sample size planning, and in meta-analysis. The cluster of data analysis methods relating to effect sizes, they're all referred to as estimation statistics. The third and final type of analysis that we'll review today is hypothesis testing. Hypothesis testing evaluates the validity of hypotheses about population parameters. It involves formulation of a null and alternative hypotheses, the selection of significance levels, and the calculation of test statistics. It helps us determine whether observed differences or associations in the data are statistically significant or whether they occur by chance. So in our example here, we typically formulate two hypotheses. One is the null hypothesis, which is what we would like to disprove. It represents the default assumption, suggesting that there is no significant effect or difference observed in the population. It often states that there's no relationship, no effect, or no difference between groups, and it's denoted with an H sub 0. The alternative hypothesis, it contradicts the null hypothesis, suggesting that there is a significant effect or difference observed in the population. It states what we expect to find and prove. It's denoted with usually an H1 or an HA. So in our example here, the null hypothesis, again, which we would like to disprove, is that there's no difference in mean externalizing problem behavior scores between males and females with autism spectrum disorder in our sample. Our alternative hypothesis, what we are testing and expect to find or prove, is that males with ASD will have significantly higher mean externalizing problem scores compared to females in our sample. The p-value is a measure that helps us determine the strength of evidence against the null hypothesis. It represents the probability of observing the obtained result or more extreme results under the assumption that the null hypothesis is true, meaning that there is no difference. A smaller p-value indicates stronger evidence against the null hypothesis, suggesting that the observed results are unlikely to occur if the null hypothesis were actually true. Typically, if the p-value is less than the predetermined significance level, which we typically use 0.05, indicating that we're 95% sure if a difference exists, then we will find it in this sample. Then we reject the null hypothesis in favor to the alternative hypothesis. So in this example here, if our p-value was less than 0.05, then we could conclude that in our sample, males did have significantly higher externalizing problem behavior scores compared to females. We will now move on to review the levels of measurement, which is essential to choosing the appropriate statistic based on your sample data. The levels of measurements that we'll review today are dichotomous, or categories with only two possible values, such as yes, no, male, female, categorical, nominal or ordinal data with more than two categories. For example, blood type or Likert scales. And the third is continuous, which is numerical data with a number of possible values, such as height or weight. Understanding the level of measurement is crucial for conducting analysis because it determines the appropriate statistical technique and operations that can be applied to the data. Different levels of measurement require different types of analysis and have different implications for interpreting those results. So using inappropriate statistical techniques for the level of measurement can lead to inaccurate results and conclusions. Therefore, understanding the level of measurement helps researchers choose the correct analysis and interpret their findings accurately, ensuring the validity and reliability of their research. The common statistical tests that we're going to review today are outlined here. Now that we've reviewed the types of analysis and the levels of measurement, we're now able to move into common statistical tests. And today we'll review correlation, chi-square, Fisher's exact test, and independent and paired t-tests. Understanding these tests is crucial as they're fundamental tools in analyzing various types of data encountered in clinical research and in practice. Mastery of these tests enables researchers to accurately assess relationships between variables, associations between categorical variables, and differences between groups. This knowledge empowers clinicians and researchers to make evidence-based decisions, draw valid conclusions from their data, and contribute meaningfully to advancements in the field. The first common statistical test is correlation, which, very straightforward, measures the strength and relationship between two continuous variables. And the effect size statistic that we typically report with a correlation is the Pearson correlation coefficient. I'll go into more of an example next, but you can see here, typically when we see something in published literature, that when we see a perfect positive correlation, the line goes up. Zero correlation, they're all over the place. And a perfect negative correlation, they're all in the same line, trending down. So a correlation example here, we have, is there a relationship between blood pressure and body mass index, or BMI? So we would then go and collect our data on blood pressure, systolic and diastolic, and BMI from a sample of adult patients. We would then make sure that we have the correct type of variables. So blood pressure is a continuous variable, and body mass index is also a continuous variable. The type of statistic that we would perform for that would be the correlation test. And we would report the Pearson correlation coefficient. This assesses the strength and the direction of the relationship between blood pressure and BMI. So the interpretation of this would be a positive correlation would indicate that a higher BMI is associated with a higher blood pressure, while a negative correlation would suggest the opposite. The magnitude of the correlation coefficient would indicate the strength of the relationship or the effect size. Another correlation example is there a relationship between exercise duration and heart rate response in patients with cardiovascular disease? So here we could monitor heart rate during different durations of exercise, for example, 10 minutes, 20 minutes, or 30 minutes. And we would do this within a sample of patients with cardiovascular disease. The two, we would use a correlation test to examine the relationship between exercise duration, which would be our independent variable, and heart rate, which would be our dependent variable. The interpretation of this result would be a positive correlation, would suggest that longer exercise durations are associated with higher heart rates, indicating a stronger physiological response to exercise. Conversely, a negative correlation would imply a decrease in heart rate with longer exercise durations. The correlation coefficient would quantify the strength of this relationship, or once again, the effect size. And I'm going to show you more examples of this statistically in just a moment. This is just so that you understand how we're starting to conceptualize what a correlation coefficient, what types of questions we could answer with this type of statistic. The next common statistical test is the chi-square test. This assesses the association between two dichotomous or categorical variables. And we're really trying to understand the proportion here. So in this example, the research question could be, is there an association between smoking status and the development of lung cancer? We'll see in our next example that there are a couple different tests that you can use to determine proportions. And the chi-square example is when we have larger cell sizes of greater than 5. And you'll see specifically what I mean by that shortly. So again, this could be, is there an association between smoking status, smoker or non-smoker. So that's a dichotomous variable. And lung cancer diagnosis, present or absent, another dichotomous variable from a sample of our patients. So we would use a chi-square test to assess the association between our categorical independent variable and our categorical dependent variable. That would be smoking status and lung cancer diagnosis. The interpretation of this would be a significant chi-square test would excuse me, indicate that smoking status is associated with the development of lung cancer. For example, if the test shows a p-value less than 0.05, it suggests that smoking status and lung cancer diagnosis are not independent, implying a relationship between smoking and lung cancer risk. This is a common statistical test that is related to the chi-square test. And, you know, pay little mind to my silly example, but I'll go into that in just a moment. This is where you're still assessing the association between two dichotomous or categorical variables, but it's when you have very small cell sizes. When I say cell sizes, it really means the number of people or fish or whatever you are looking into. So small sample sizes, a Fisher exact test is particularly useful when sample sizes are small because it provides an exact probability rather than relying on approximations like the chi-square does, which may not be accurate with small samples or when expected cell frequencies are low. So by accounting for small sample sizes, Fisher's exact tests help to reduce the likelihood of type 1 errors or false positives and type 2 errors or false negatives, ensuring more reliable inferences about the association between variables. So in summary, a Fisher's exact test is a valuable tool for analyzing categorical data, especially in samples where the small and expected cell frequencies are less than 5. And it provides a more accurate assessment of association between variables while accounting for limitations imposed by these small sample sizes. So again, in our silly example here, we have, okay, the sex of the fish, male or female, dichotomous variable, and we'll say this a different way, how attractive they think they are, yes or no. And we only have 5 fish in there. So we're comparing the females to the males, and we would have to use a Fisher's exact test in order to interpret this result. That fish does not look very pleased with his appearance. The next statistical test is the independent samples t-test. This compares the means between continuous variables in 2 independent groups. So for this, a research question that we could ask for an independent sample t-test, and again, I'll give you more examples after this and show you exact data. But this is to help you understand that we could ask a question like, is there a significant difference in the mean blood pressure between patients with hypertension who are taking antihypertensive medication and for those who are not? So we would sample a patient of populations diagnosed with hypertension, and we would have 2 groups of patients. One group taking antihypertensive medication, which would be group A, and another group who are not taking any medication, group B. So the variables we have here, the independent variable is medication status, group A or group B. That's the categorical variable. The dependent variable is blood pressure, which is continuous. So in our data collection, we would measure our blood pressure in patients for both of the groups. We would conduct an independent sample t-test, and we would compare the mean blood pressure values between group A and group B. We would calculate the t statistic, which indicates the difference between the means of the 2 groups relative to the variability or standard deviation within each group. We would determine the p-value associated with the test statistic, which we would estimate at 0.05. So if the p-value is less than the chosen significance level, It suggests that there is statistically significant difference in mean blood pressure between patients taking antihypertensive medication and those who are not. Further interpretation can be done based on the direction of the difference. If the mean blood pressure is higher in one group compared to the other, this may have clinical implications for treatment, effectiveness, or patient management. So in summary, the independent samples t-test is used to assess whether there is a significant difference in the mean of a continuous variable between two independent groups. In this clinical example, it helps to determine whether the use of antihypertensive medication is associated with significant differences in blood pressure among patients with hypertension. We've just learned what statistical tests we would use to conduct within independent samples, but what if the means of our two groups were related, so not independent of each other? Here we would conduct a paired samples t-test. Compares the means of continuous variable with the same group before and after an intervention. An example here would be, is there a significant difference in blood pressure before and after a mindfulness-based stress reduction program among patients with hypertension? We would sample from a population of patients diagnosed with hypertension and patients who are enrolled in an MBSR program. The dependent variable is blood pressure, measured before and after the program. So here we would compare the mean blood pressure levels before and after this intervention within the same group of patients. Their scores are not independent of each other. They're related. We would conduct the paired sample t-test and we, would choose our significant levels of 0.05 and indicate that there is a statistically significant difference in mean blood pressure before and after the MBSR program. So now we get to conduct analysis and interpret results as a group. We're going to put our knowledge to use. I can't see any chats or anything, but this will go through quickly and it's just a fun exercise to do. So whoever is, Carrie is monitoring the chat, you can just go ahead and type in what you think the correct statistic we would do to answer the question. Is there a relationship between parent stress scores, which is a continuous variable, and their child's externalizing problem behavior scores, which is also a continuous variable? So the question is, which statistic would we use to answer this question?
I didn't even have to hum the Jeopardy theme. You've got
Excellent.
some, yeah, I don't know if you can see, you've got some answers coming in.
I cannot see the chat, unfortunately, because
Okay,
I can only see my screen.
we have correlation tests. Several people have said that.
Excellent. Several
And let's
people
see.
are correct.
Awesome.
Excellent. So we would use a correlation for this, where we're comparing the mean scores between two continuous variables. We would see here that we have our mean for child problem behavior, our mean for parent stress. Can you see my mouse moving?
Yes.
Okay, great. Here we have our Pearson correlation coefficient, which is 0.401, which is positive. And we have our significance p-value here, which is 0.000, and positive, significant. The interpretation of this result would say that there's a significant and positive correlation indicating when child problem behavior goes up, so does parent stress, which I think makes perfect sense.
Does anybody have any questions they want to ask or before we move on, just because maybe I see a few faces, ones I can see. All right. Well, if you do, or if you want to raise your hand, let us know.
Great,
Thanks,
yeah,
Cassie.
and also as you digest this, if anyone has questions after the presentation, feel free to send me an email as well. All right, moving on. The next question that we are going to answer is there a difference between males and females, which is a dichotomous variable, and they're externalizing problem behavior scores. So we have a dichotomous variable that we are comparing mean scores between two groups. Which statistic do we use to answer this question?
We have a few answers. We have t-test is the winning answer.
Excellent. Love it. So this is going to be an independent t-test because we're comparing the mean scores between two independent groups, males compared to females, on a continuous variable, which is their child problem behavior scores, or externalizing problem behavior scores. So the first thing we do is we go, over here, and we look at our descriptive statistics. And we can see that for males, they have a mean of 26.75. And for females, they have a mean of 30.8. And for this, the higher the score, the higher the externalizing problem behavior. So here, we're able to go down into our lovely test statistic, which gives us our t-test here and our significance value of 0.001. The interpretation of this is that in our sample, females with autism spectrum disorder have significantly higher externalizing problem behavior scores than males. Conscious of time, so I'm just going to go through this last one quickly here. So this is our last question. This is our last question. Is there a difference between males and females? Again, dichotomous. One variable, males or females, with autism spectrum disorder who engage in self-injurious behaviors? Yes or no? We have two dichotomous variables. Which statistic do we use to answer this question?
I'm scrolling down. I'll let We've got chi-squared, and one is chi-squared or Fisher's, depending on the sample size.
Beautiful. Excellent. So here we would use a chi-square or Fisher's exact test, depending on the sample size. Excellent. We have, so the first thing that we're comparing the proportion between two groups. And we would first go up here to our 2x2 matrix here, and we would look at our cell sizes. So for males who do not have self-injurious behavior, there's only two, with the majority, 56, having self-injurious behavior. And females, none of them, excuse me, my mouse keeps going away. We have a very small sample size here of 0. So we would go down and look in our test statistic here that we have just conducted. And here is the result for a Pearson chi-square test, which if we reported this p-value would be incorrect because of our very low cell sizes, as we see here, the proportion of people within each category. So here we would report the Fisher's exact test with a p-value of 0.550, which is definitely not less than 0.05. And our interpretation would be, in our sample, there is no significant difference between males and females who engage in self-injurious behaviors. We would indicate that our sample was too small to draw more conclusive results. So what do we do with all this? We pull it together and we can present our results either in a table 1 for our manuscript or presentation. And here you can see that we have, again, we have a full sample of kiddos with autism spectrum disorder, and we've divided them up into a profound and non-profound based on specific clinical criteria. And here we have our test statistics, which has our t-tests and chi-square tests for each one of our variables here. And we also have our p-values here indicating where there were statistically significant differences between groups. So that's just an overview of, so what, who cares? What do you do with all this? And this is how we're able to look at this and get a very good understanding of what our sample looks like for this particular study. That is where this is my final slide. And now I'm going to turn this over to Brianna Taylor, who's going to review the assumptions, violations, and solutions. So thank you all for your attention, and please feel free to chime in at the end with questions or email me with questions.
And I think Yvette wanted to take a minute to introduce
Yes,
Brianna.
yes. Thank you, Kasi. I just wanted to tell people that the slides are available on our website. If you are like me and may want to review that, and even the recording will be available on the ECHO website. So thank you, Kasi, and it is my pleasure to introduce Dr. Brianna Taylor. She earned her PhD from the University of Pittsburgh and is currently a faculty member at the Root Institute and an affiliate faculty member at the Maine Health Institute for Research. Her research focuses on associations between sleep patterns and both behavioral and mental health. Her current focus is to examine sleep patterns and circadian physiology as predictors of adaptive functioning in children and adolescents with autism spectrum disorder. And you can see that Kasi and Bree work together on their shared interest in autism spectrum disorder research. Thank you, Bree.
And I'm just going to let you know where we're at. We have about 20 minutes before the hour.
Okay, great.
So,
Can everyone see my screen here? I tried doing the slideshow, but then I can't see my notes. Can everyone see basically the slide? Or is it? Is that okay?
Yep.
yeah.
Yep.
Yep.
Okay. Great. Great. Okay, so we're actually going to now be shifting a little bit. So we didn't have a case in particular. So we thought one of the best things that we could do is actually go through checking assumptions, which is something we don't typically do when we're giving a very broad overview of stats. But this gets into a little bit more of the nitty-gritty in terms of how do we actually look at our data to determine if chi-squares or t-tests are valid approaches for describing differences in our sample or answering our questions. And then what do we do when they're not? And so we do this. This is known as checking assumptions. And assumptions are basically just conditions that our data needs to meet in order for a test to produce a valid result. And these conditions vary by statistical test. Each one has different ones. Some of them overlap across different tests. And most of the assumptions have to do with how the data are structured, how they're distributed across participants or observations. And for the test we're talking about today, we can test if our data meet these assumptions, mostly just through critical thinking or visually inspecting our data. And I guess one of the most important takeaways here is that when an assumption is violated, the test can be misleading. So it's really important to understand these basic rules about test appropriateness and the importance of looking at our data before we start running analyses. And then, of course, what can we do when our data don't meet these assumptions? We're going to start by looking at chi-squares. So just as a reminder, what Kasi was explaining, chi-square tests are used to examine whether there's an association between two categorical or dichotomous variables. And the first assumption that the chi-square test makes is that each observation is independent of every other observation. So simply put, this means that one, each data point should come from a different participant, i.e., no person should be counted more than once. And two, data points should not influence or be influenced by other data points in the analysis. And so to illustrate this, to illustrate a scenario when this assumption might be violated, I'll use an example from the type of research that Kasi and I do. We might be wondering, my work has to do a lot with sleep, so Kasi and I collaborate on sleep and autism research. We might be wondering whether it's significantly more common for a child with profound autism to have a major sleep problem relative to children with autism that isn't profound. So we can define profound autism as meeting specific criteria. So we typically describe it as having co-occurring intellectual disability or being minimally verbal. And once we define the group criteria, we can establish membership dichotomously fairly well. But maybe we haven't established how to define major sleep problem. We might know from the literature that a nighttime awakening that lasts at least 30 minutes is very problematic. But maybe we have 14 nights of data, sleep data. So we can look at that data and code each night as a dichotomous variable. 0, no awakening greater than 30 minutes, or 1, yes, there was an awakening greater than or equal to 30 minutes. And this can then yield a set of binary or dichotomous variables for each participant. So now we have group membership as a binary variable, profound or not, and our sleep problem variable, yes, no, for each night of data collection. But can we use this in a chi-square to test if sleep problems are more prevalent in our participants with profound autism based on the way that we've set up the data so far? That's my one question to the group, so I can't see the chat. If you're thinking no, that is correct. So, and this is because our sleep observations are nested within our child participants and such that our nights of sleep data are dependent on one another. So they may be discrete nights of data, but we know that one night can impact the following night and can also be influenced by a previous night. So we can't treat them as independent observations because when we do this, we're actually artificially inflating our sample size, and this can give us very misleading results. And so in this scenario, what we could do is something very simple and just simply aggregate the child level data by creating a single dichotomous variable based for or categorical for each child based on our 14 nights of observations. We might define a threshold for what constitutes an actual sleep problem. So in this field, we typically say greater than or equal to 30 minutes of wakefulness after sleep onset for at least 3 nights a week. Could be labeled as an actually profound sleep problem. And so this allows us to preserve the independent observations and describe our data accurately as we've defined it. But that's essentially it. So it really depends on our goals. And we have to be mindful of how we're operationalizing our categorical variables. And what we're losing here, of course, is within subject variability, which may be important depending on your question. Another option we have is another option when we have dependent observations nested within individuals is to use some form of more advanced modeling technique. So if we're interested in that night-to-night variability. And so this would go beyond simply descriptive statistics, and we would use something like multi-level modeling, which I'm not going to go into too much detail here, one for time, but I think that's probably going to be in a subsequent biostatistics session. But essentially it allows you to look at both within child effects and then between child effects, and essentially look at a little bit, answer questions beyond what does our data look like, but address questions such as how much do differences between children matter versus differences from night to night within the same child. Okay. So chi-squares also make an assumption that there are adequate cell counts across chi-square cells. So Kasi got into this with talking about the difference between a Fisher's exact test versus a chi-square test, so I won't spend too much time here. But so she mentioned cells. And so in the most simple 2x2 matrix we would have for a chi-squared, we would have a predictor variable and an outcome variable, each with 2 levels, and this gives us 4 cells. And so we need enough data in each cell in order to make the math of the chi-square test work. And essentially, whether or not the difference in the groups are real or if they're just there due to chance. And so to do this, basically, we need to estimate what's known as expected counts, expected cell counts. And so this is really what the data would look like if everything was due to chance, or sorry, not what it was due to chance, if there were absolutely no relationships between our predictor variable and our outcome variable. what would it look like if there aren't systematic differences across our groups? And what the chi-squares test does is it compares the null hypothesis version, basically, of the data that Kasi described to our actually observed data. And so this is a very long-winded way of saying that if we have very small numbers in these different cells, a difference between our observed data and our expected data or expected counts based on if there's no relationship, any small difference there could look very big and actually lead to more exaggerated differences, and so misleading results from that analysis. And I think we're going to be sharing these slides with people as well. So any information that's a little bit too detailed, you'll have that. You can also ask any follow-up questions. So this is a really common problem when you are looking at rare outcomes, rare conditions, or rare predictors. And so one thing that we've already mentioned, you can look at the Fisher's exact test. Another thing you might do is actually a logistic regression. And without going into too much detail, this is an option because it doesn't have the assumption of the expected cell sizes. It is estimating probabilities. It does have its own assumptions, and small cell sizes can be a problem here. So it's really weighing what's appropriate. But it will yield something like an odds ratio, which I think clinicians in this group are more familiar with. Another benefit of that type of analysis is it does go beyond description and describing your data. You can adjust for other factors that you think might be influencing your outcome and include what's known as covariates to look at whether variables such as age or gender influence that relationship between your predictor and your outcome. And then another very simple solution to this would just be collapsing categories that might be small. So in my research, I have the common problem of a rare sleep problem phenotype. So many children on the spectrum, but not a ton, have early morning awakenings. So rather than waking up throughout the night periodically for prolonged periods of time, they might wake up at 3 in the morning and not go back to sleep. So it's a small group on its own and then very hard to understand and compare against other groups. But what we can do is look at it in relation to these awakening children and combine them together because they both fall under this umbrella category of sleep maintenance problems. So this is great for increasing cell size, but it just one needs to do it very deliberately, and it has to you have to have a very defensible reason for combining these groups and justify collapsing across different categories. So the final, sorry, did I move on already? No, so now we're just going to turn to t-tests here. And so one key assumption for t-tests is something you already know by now, and that's that the outcome variable must be continuous, meaning that it can only take on a numeric value on a scale, and the differences between the values must be meaningful. And this matters because this assumption, the assumption of t-test is, the t-test relies on means and standard deviations. So variables such as sleep duration or parenting stress would be appropriate here. Of course, binary or categorical variables are not, for reasons that I think are fairly clear. We can't meaningfully generate means and standard deviations for categorical variables like gender or race. But we have to be careful about other variables like count data. So in my data, the number of nighttime awakenings is a count variable and not appropriate for a t-test because it can only take on whole numbers, and the data is often very skewed. We have children with a lot of awakenings and then many others with few to none. So when you generate means and standard deviations based on that type of data, it really loses its meaning. So for a solution, we've already talked about chi-squares for dichotomous or categorical variables, but others like count data There are other tests that compare individuals based on rank order rather than means or standard deviations. And so I won't go into detail, but we can talk about them offline if that's of interest to people. And then there are other tests that really account for data when there are very few occurrences of the outcome that you're looking at, like Poisson regressions. Poisson. And so the next assumption that we're going to look at is independence of observations. So similar to chi-square tests, each data point needs to, in the t-test, is intended to provide unique information and is not influenced by other observations. In an independent samples t-test, this means measurements from participants in one group should not be related to measurements from participants in the other group. So one participant's pre-intervention scores are not compared to that same participant's post-intervention scores in an independent samples t-test. However, in a paired sample t-test, this is appropriate. The independence with paired sample t-tests really refers to the pairs themselves. So the two observations within a pair are expected to be related, like pre-post intervention, or if you're looking at couples and one partner versus another. And so really violations here involve picking the incorrect or inappropriate test. And the final assumption with t-test that I'll go over is really just the distribution of the data. So as Kasi already mentioned, the t-test relies on data that show this normal, nice bell curve distribution. And so it means no heavy skew or really influential outliers. But of course, there are definitely routes that we can take to make the data usable for a t-test if it doesn't necessarily fit this perfect bell curve. And a couple are transformations. And this is probably getting too much into the weeds, but it's really applying a function to your data to normalize it. It doesn't change the meaning of the data, but it makes it fit the bell curve better so that a test like this can be used. And then there are other tests as well called non-parametric tests, which don't make an assumption about the shape of the data like this. So in summary, every statistical test has assumptions that need to be met for its results to be valid. By carefully checking our data, understanding these basic rules, we can ensure our analyses are accurately reflecting real patterns in our data. So we're just butting up on time with 4 minutes to spare, and we're happy to answer any questions.
Pretty impressive. I don't know if you want to say anything, Yvette.
Yeah, just that this is a great segue for the next presentation by Dr. Peter Callis about regression. And these two lectures, this Basic Stats 101 and kind of follow-up stats next month, were topics that were asked by our participants. So we know that there's interest by our ECHO participants to understand these. So we appreciate you guys giving us this great background and understanding. And just, the slides are going to be available, the recording is going to be available, and consult your friendly biostatistician in your study team is usually my top recommendation.
And, we're looking for a case for February. And one way we could do that is if you have questions about something you're working on, maybe we could take a couple different examples and do some of that consulting in front of other people is a great way to learn. So reach out to one of us. Meredith, myself, Yvette, Kim, if you have projects that you're working on that you think, ooh, I wish I could dig in a little bit, that might be a really good way for us to cover a case next time. So feel free to reach out. And yep, there's the slide. February 25th will be part 2. And I guess if there's no burning questions, we could give people 2 minutes of their day back. But thank you so much for taking these very complex issues and helping us to dive into them.
Yeah, excellent.
Thank you. This was great.
Yeah, thank you.